And without further ado, we'll get to our program. So Dr. Ilke Demir is a senior staff research scientist with Intel Corporation. He's going to be speaking to us about deepfake dystopia and how to battle it, and sharing some cool tech and ideas and research that's happening in that area. Thank you.
Thank you for the nice introduction. So let's
This
start.
is a deepfake with my voice and Nicolas Cage's face. And there are thousands of others on the internet. How can we trust our eyes in a world of synthetic media?
Well, welcome to my presentation. And it is great to give this presentation in person so that you can actually see me and my deepfake at the same time. So without further ado, thanks Deepfake Ike, and welcome to my presentation about building trust in a synthetic world with AI. I'm Ilke Demir, and today I will introduce our responsible AI approaches around deepfake detection and generation. Before we start, I would like to thank ACM Orange County chapter for inviting me to give this talk. I'm very happy to be here in person, yay. This talk is also made possible by ACM Distinguished Speakers Program with a mission to help computing professionals to connect, create, and advance together. And if you want to have more information about the program, the link is there. So who am I to begin with? I got my bachelor's degree in computer science with a minor in electrical engineering from Middle East Technical University in Ankara, which is also my hometown. And my interest in vision and robotics sparkled there in an internship about swarm robotics, actually. Then following that interest, I started my PhD in computer science in Purdue University, joining the CGV lab. And my thesis was about proceduralizing the world, which means like, can we digitize everything we see around us in 3D? Then I had a very beautiful internship at Pixar as a graduate intern, and it is indeed one of the most magical places to work at. Fast forwarding, after I earned my PhD, I joined Professor Ramesh Raskar's group at Facebook as a postdoc. We started investigating how we can apply main pillars of proceduralization and deep learning and generative models into different areas like satellite imagery understanding or deep learning for human understanding in VR, etc. So these are all different projects that we worked on. And most of them are open source, so you can just like search for it. That brings me to previous years. I worked in a startup. I was also in UCLA IPAM as a visiting scholar, etc. Then bringing me to today, where I found myself in a research heaven at the world's largest volumetric capture space, capturing 270 gigabytes per second of data at Intel Studios. Now, let's return back to the journey of generative models and deepfakes to see how they will end up in our studio. If we take just a moment to go back to basics, you know, in deep learning, there are different learning models, discriminative models versus generative models. Discriminative models are those models that are doing traditional computer vision tasks such as recognition, classification, segmentation. So given this beautiful image of a cat, what is it? What is inside it? Or how we classify it? This is discriminative models doing analysis. Then there are generative models that are doing synthesis. So if you are asking what is this in the first part, in the second part, we are actually asking this is what. So given a distribution of many things, can you create new samples from that distribution? Those are mostly generative models. The main idea for generative models, we want to go beyond associating inputs to outputs, but we want to understand high-dimensional complex probability distributions, like how this data how we can model this data from just samples so that the distribution gives us realistic samples. We want to discover the true structure of the data, or we want to detect surprising events in the world based on that distribution, or we want to see missing data if we just have the samples if the data manifold, let it be images, let it be shapes, let it be cats, if that data actually provides us with the missing samples. So there are three main types of generative models. These are very, very basic types. If we want to categorize, there are many different versions right now. But if we go to the basics, there are autoregressive models, which you see the example here. If we are generating elephants, can you see? Yeah, okay. If we are generating elephants, like we have some elephant-like structures, but maybe they have like 5 legs or no trunks or something like that. These are mostly modeling the class conditional probabilities explicitly. So each probability can be a neural network by itself or a simple probability. Then we have variation autoencoders. These are mostly taking the data, encoding it into a representation in the latent space, then decoding the data to have the actual distribution. These tend to create some blurry samples like this. But again, this is like the very basic version because the distribution convergence between the target distribution and the given distribution is not always perfect, so the convergence is not really going to a non-existing perfect distribution. Then finally, they have generative adversarial networks, which you see some of the samples here. So this is like a game between a generator neural network and a discriminator neural network, where generator is taking this uniform noise and trying to shift that uniform noise to a distribution that is covering the distribution of real samples. If we are again creating cats, given many cats, how we can shift this random input to cover that distribution. Whereas the discriminator is taking all of those samples and saying whether they are fake or real. So seeing this cat, it is saying, okay, this is a real one. The another cat is a fake one, etc. So generator is trying to fool the discriminator, and discriminator is trying to distinguish between fake and real samples. So why we see these? Because these are all very related to deepfakes, and this is the basic models that are behind creating those deepfakes. Now, using all of those, of course, it didn't stop with just GANs, just generative adversarial networks. Now we have like LSGAN, PGGAN, Wasserstein GAN, Cycle GAN, and like all of those different GANs actually create made it commonly available and efficient to train new deep learning models on more data, and such democratization of AI enabled the creation of deepfakes, very photorealistic deepfakes. Deepfakes are synthetic images or videos created by advanced methods where the actor or the action of the actor is not real. As you can see in this compilation, they were actually like they are very realistic, and they were initially used for photorealistic avatars or AR VR productions, but of course it became a bad tool to actually fool people or misguide people. You can even see here my actual photo and my Nicolas Cage version deepfake. Since the introduction of GANs in 2014, the quality, the realism, the control over deepfakes have increased significantly. And it is amazing to see such high resolution, consistent images of people who doesn't exist. And now we are even able to change the head pose or the gender or the age or the illumination, or like we are getting more control and more editing power over those deepfakes. So although this technology has been developed with positive intent, it also attracted malicious users to exploit deepfakes for political misinformation, impersonation, forgery, and pornography. And the more we see them online, the more we hesitate to trust any media content that we see online, right? And this threat to information integrity has consequences in privacy, in law, in politics, in security and policy, and it poses a threat for social erosion of trust. So you won't be believing anything you see, even if it is real. Of course, in the literature, there has been other some approaches to detect deepfakes. It's not just generation, and different data and image-based representations are investigated. These include, some of them include like compression artifacts or boundary artifacts or any artifact of fakery. It can be like symmetry artifacts, etc. So what gives us the fake images? Then there is, on the other hand, there are other approaches that are looking what is unique in real videos, which is not replicated yet in fake videos. For example, the heart rate, the phoneme matches, the gaze detection, etc. These are all looking for authenticity signals in humans. So today we will look at those, after these features, they are either used to train a model like a CNN, RNN, a deep neural network, or there's also other approach of looking for big corpus of data where search engines are looking whether that video or image has been seen before in somewhere else. And after either from the model or from the search engine, there is a classification, then then it is decided whether it is fake or not. So today we will mostly look at these deep biological detectors with different features and different models. So I will start by introducing FakeCatcher, our world-renowned deepfake detection algorithm. You have probably seen it in any of these news articles. They keep appearing everywhere in different languages. But if you have seen any deepfake detector with heart rate, it is probably FakeCatcher. The intuition behind FakeCatcher is simple. So most detection approaches are looking at fakeness, what faults are in fake data, what are the artifacts of fakery. But our approach, we ask the question if there is any intrinsic watermarks of being human. What makes us human? What gives away, what signals give away that we are human? Well, if you have watched the OA, Dr. Happ mentions that heartbeats are like signatures for people, and it's like more unique than a fingerprint. I don't know. Should we believe him, or like, why is this even related, right? The answer to our previous question is actually yes. So we should actually believe Dr. Happ in this case only. As our heart pumps blood, that blood goes to our veins, and our veins carry different levels of oxygen, and that oxygen difference actually creates some changes in our skin. So the subtle color and motion changes are called photophotorealism for the color change and barysocardiography for the motion change. So from any video, we can actually detect heart rate. So in this case, we are actually using photophotorealism, PPG for short. I will keep saying PPG. It is this. And no generative model can create deepfakes with consistent PPG signals yet. So that's why this is our authenticity clue as of now. So the first question that we asked about the PPG signals and deepfakes is that given n pairs of fake and real videos, can we find an implicit indicator of biological signals? We first looked at those signals on original and fake videos. And for the original videos, you see like it is periodic, it is following the heart rate. Even if it's not exactly the heart rate, the very true heart rate, there is still some bounds and some periodicity to the signal. But for fake videos, it's everywhere. 1 second, your heart rate is 70, then it is 200, then it is back to 10 or something, you know? So it's not really reflecting of the actual PPG signal that you should have. So how can we use these signals? We looked at many different configurations. And the answer to the question that given n pairs of fake and real videos, can we find an implicit indicator of biological signals? The answer is yes. So based on several experiments we conducted on these signals and their derivatives, such as their temporal and spectral components and correlations and all those different experiments, we found out that the pairwise cross-spectral densities actually give 99.39% accuracy for detecting which one is fake, which one is real. Again, this is the pairwise separation task. This is not the generalized deepfake detection, but this closed form formula is just a closed form formula. There's no deep learning, there's no learning. It's just like given two videos. Just looking at the pairwise cross-spectral densities of PPG signals is very accurate. Now, of course, the follow-up question would be, given n pairs of fake and real videos, can we train a detector to learn this space, right? Because it was for pairwise separation task. Now we want to generalize this. And the first way to generalize it, can we actually learn those signals, right? In order to generalize the formulation, we extract several relevant temporal and spectral features from PPG signals, and we train the basic kernel-based SVM on a large data set of fake and real videos, and we obtained 75% accuracy. So this is not really very accurate because just imagine you see like 4 different Scarlett Johansson videos on YouTube, and the detector says all of them are fake, whereas one of them is real. So it's not really that accurate, 75%, right? How can we actually improve that? As we are using interpretable features, we actually wanted to understand the feature space. So we applied some source separation techniques such as PCA, LDA, and CSP to our PPG feature space. And it revealed that the solution space was not linearly independent, and it was very high dimensional. So what we do in these situations, we throw a neural network to it. So using the same PPG maps with a very simple CNN that you see here, we obtain 96% accuracy with the same data set split. So this is the foundation behind FakeCatcher. Now, of course, high accuracy on one data set is never enough to validate an algorithm. So we evaluated on 5 different data sets with additional cross-model and cross-data set settings and with additional post-processing artifacts. So we added some Gaussian blur, we added some the frame interlacing, etc. And even in those cases, we have okay accuracy compared to other methods. Then we looked at other data sets, and the one that I want to mention here in red is that the others are mostly academic data sets where the generative model is known, there's no compression artifacts, there's no noise, etc. But the deepfakes in the wild data set is an actual in the wild data set with everything you can imagine from YouTube, Twitter, or like research presentations or any medium that you see deepfakes on, it is in that data set. So in the wild data set, we have 91% accuracy, which is still very, very useful in this context. We also experimented with different facial regions and compared to baseline methods with complex network architectures such as exception, inception, and others, and we beat them with more than 8% difference in accuracy. And for FakeCatcher and for future deepfake detection research, we also released our deepfakes in the wild dataset to serve as a benchmark dataset, including real-world cases like unknown generation, unknown compression, occlusions, motion, makeup, illumination artifacts, everything that you can think of. Now, we took FakeCatcher and we built the first real-time deepfake detection platform on top of that, thanks to specialized Intel architecture, operations. So it uses, so we first decode and pre-process. Then we use face and landmark detection models, which are openly available in OpenVINO AI models. Then we use those face detection and landmark detection outputs to create PPG maps and to run inference with the pre-trained PPG model. Then we encode and stream that. And it uses, as I said, like OpenVINO AI models, the Intel AVX 512 and Intel AVX 2 for optimized image processing, computer vision, and deep neural network operations. It also uses deep learning boost VNNI operations for the models. And the open source framework is based on GStreamer. This is a demo of the platform. So as you see here, we have the segment label. This is for every window that I talked about. So it is either 64 frames or 128 frames. Then we have the aggregated video confidence here, video label and the confidence here. You can see the frames per seconds, and you can see the overall accumulated confidence here. And this is basically real time, running inference real time, and we can go up to 72 concurrent detection streams on Intel Ice Lake, on Intel Xeon processor. Now, I want to pose another question. FakeCatcher may inform you whether a video is fake or real, but where do these fakes come from? Or can FakeCatcher find their source, like which GAN is used to generate which video? So in the literature, there are several articles that propose the generative models leave some residue, leave some fingerprints, and these can be interpreted to trace it back to the actual GAN that created a video. These mostly investigate the image domain, and then they try to classify the generative noise blindly without any projection to any signal domain by a set of known models like ProGAN, StarGAN, StyleGAN, etc. But what about our domain of face videos? Can we use such generative residue for deepfakes? Well, in contrast to FakeCatcher, we want to interpret generative noise of specific models as a deformation in the biological signals. So if you look at these images from real video versus the different different deepfakes generated by these different GANs or these different generative models, you see there is some difference in the image domain, in video domain, right? But it's not really that clear. You can see that they are different, but you don't really see a unique signature. But if you interpret these residuals by projecting them to the biological signal domain, then you can really see that the signatures are different. So you can see this residue changes, and we actually want to use that residue for source detection for deepfakes, not images, but deepfakes. This is very similar to FakeCatcher. So we extract PPG cells, we do a multi-class classification instead of binary classification of PPG cells. And then since the signals are more complex than FakeCatcher, we are using a more complex CNN architecture, but it's just a VGG19 backbone. Then we aggregate them into video predictions by log of odds. Now, if you look at the results, in Face Forensics++ dataset, where there are equal number of real and fake videos from 4 different models, we can find the correct source of a deepfake video by 93.39%. So this is the correct classification to see whether which deepfake came from which GAN. Moreover, the source detection actually increases our fake detection accuracy. So on the same data set, we have 96% accuracy, but source detection have 97.29% accuracy for fake detection, which increases the FakeCatcher's detection accuracy. Finally, we want to pose this as a way for continuous detection and integration. For example, if we just take 1,000 fakes from a completely different data set, which is CelebDF, as a 6th class, and we retrain the model, we see that the accuracy is very similar from 93, still 93. And on the CelebDF, which is a new data set that we added, we still have 92% accuracy. This is very important in terms of not needing the originals in CelebDF. This is just 1,000 fakes from this new data set without the need of the originals. So this means that if we have this platform for source detection and fake detection, then we can just, if there is a new, very super realistic GAN is coming, we just take the fakes of that new GAN, retrain the model, and we can detect them without the need for their originals. We also did some ablation studies. I'm passing these for time and more experiments. All of them are in the paper. Okay, now another topic, deepfake detection with gaze tracking. We discovered that PPG signals are a nice authenticity indicator, right? Like they give away the heart rate, so we can trust them. Is there any other such biological signals? Well, gaze and eye information is one of them. So what about the eyes? As the eyes are the mirror to the soul, we investigate the truth in the eyes of deepfakes. Comparing real eyes to the fake ones, we observe that there are significant visual and spatial artifacts, as shown here with, again, like four different generative models, as you see here. The difference between left and right and the difference between landmarks is obvious, and we can group them as symmetry artifacts. Moreover, anomaly also occurs in gaze behavior. So we as humans, when we are looking at a point, our gazes converge at a point. Even if it's a very far point, they are coplanar, but they are not like this. Our gaze vectors are not like this. But for fake videos, they are like that. So they are either not converging or they are like not coplanar at all. In addition, if we look at the 3D gaze points of those, you can see that if we are looking like 3D point, 3D point, 3D point, 3D point in a uniform way, the fakes are either noisy, they are like that jiggling in the 3D gaze points, or they are missing some paths. If there's a jump, if there's a saccade from from one way to another in our gaze direction, then that is missed, etc., and they are not uniform. So these are all giving away the deep fakes. We also evaluate their properties in temporal domain for fake and real videos. For example, real gazes cover more vertical and horizontal range than fake ones. Again, the fake gazes have those like shaking like noise, as you see there. And the fake iris sizes can differ by 30 millimeters square and pupil sizes by 14 millimeters square for the same person. And our eyes doesn't change that much, right? Like if they may dilate or go smaller, but not that much, right? But for fake ones, that is the case. Such signal properties are also detectable in the spectral domain, not only the temporal domain. So you can see that like the changes for real versus fake are really visible there. So we took all of those. We formulate all of these like visual, geometric. Oops, sorry. Yeah, we formulate all of these visual, geometric, metric, temporal, and spectral features together, all eye and gaze-related consistency and coherence measures together, and we create those gaze signatures. Then we train a neural network to classify those gaze signatures as fake and real videos. These are like normalized features with equal and trained on equal number of reals and fakes. The dataset split is like 70 to 30, and training takes short time. Because we have this powerful representation of gaze signatures, we can actually use a simple neural network instead of going very deep, very exception inception like or a ResNet like a very deep neural networks. We can actually get away with simple networks. If we look at the results, our eye gaze-based fake detection algorithm achieves 99.27% accuracy on a new data set called deeper forensics, and 92.48% accuracy on face forensics plus data set, which was the previous data set that we showed FakeCatcher on. We compare our results to the detection results of 11 different deep and biological fake detectors. It overperforms almost all of them except FakeCatcher. So you may ask why that is the case. Why FakeCatcher is better than eye gaze-based detection? Well, there are different reasons for that. First of all, eye gaze-based detection is just looking at this information, nothing at all. But FakeCatcher has much more information from the skin. It's like 32 different signals, all from different regions of interest. So we looked at their failure cases, and they're actually complementary. So on the left, the eye gaze-based detection correctly classifies a fake video, and it correctly classifies a real video on the right. But FakeCatcher fails due to physical or digital corruption on the skin for both cases. So it may be too much makeup if it's the real video found as fake by FakeCatcher, or it may be too much blur if a fake video is found as real for FakeCatcher. So they are actually complementary, and that pushes us, that inspires us to do those ensemble detection platforms. And this also provides a way for algorithmic consensus, right? We are not just trusting FakeCatcher, we are not just trusting eye gaze-based detection, but we are providing the user with like all of these different approaches and algorithms to provide algorithmic consensus about whether a video is fake or not. Now, we talked about deepfake detection a lot, but can we do responsible generation? Can we use deepfakes responsibly? First case that I will discuss is, can we mix multiple faces to prevent impersonation? So, up to date, all deepfake generation approaches need a source and a target. So I'm talking like this, and you are taking my face and mimics and sound and making like Mark talk like me, right? That is like the evilness behind deepfakes. It's the impersonation of people. Whereas like, so it's either like a autoencoder based or mask based or retargeting approaches. They are all source to target. They are mask dependent. They are either mask dependent the masks are discrete. So can we actually do it in a responsible way? Can we eliminate the impersonation part? Well, if we, instead of trying to mimic someone, trying to replicate someone one-to-one, can we actually make a human soup? We can take my nose, your mouth, your ears, your eyes, and we can make a human soup. And that won't be impersonating any of us one-to-one. And that would be a more responsible way of making deepfakes. How do we do that? So if we try to take eyes from this face, nose from this face, and all these orange parts from these faces and try to copy paste or blend, there is this monster looking like structure here. I can't even call it a face, but it doesn't work. However, if we use mixin, I will talk about what mixin is, but the approach is called mixin. We actually learn composition and style jointly. We create these fuzzy masks from the different mask parts. We learn to create these fuzzy masks. And on top of that, we learn to create this style based on different masks so that we can create this human soup face. So if you look closely, the nose look like this nose, the hair look like this hair, etc. Without going into much details, we use a structure generator that encodes all of these different mask parts and creates these fuzzy masks from different masks. Then we have a style generator to encode all different styles per region and use it as a style matrix to create from these fuzzy masks a real face. And it generates these new multi-sourced humans. So you can see that different face parts are replicated accurately. You can mix genders, you can mix different face colors or poses, etc. And all of those results are not impersonating anyone one-to-one. They are basically multi-sourced images. We also compared it, so it is the first multi-source deepfake generator, so we cannot compare it to others, but we compared it to the single source ones in an incremental way. And as you see, our results are both quantitatively and qualitatively more realistic. So you can look at the paper for all of these, like PSNRs, RMSEs, FID scores, etc. But I want to just like get your attention to this column. So even if you apply sequentially, changing part by part, like changing nose first, changing neck then, etc., there is like these blending artifacts that like nose has different color. I'm not sure whether you can see it from the screen, but nose is actually very different from the cheeks, or here like there is a phantom mustache here, or the hair is different color, etc. So that's why mixed synthesis is actually better. So what next? What can we do? Can we actually use generation to evaluate different defect detectors? So I put this, by the way, to show adversarial generation. I don't know whether it is adversarial enough. It's not a lion, but it still tricks the face recognition algorithms, maybe. I don't know. Anyway, so we can actually do adversarial generation for detector misclassification. So for these state-of-the-art deepfake detectors, DenseNet, Inception, ResNet, etc., they find that fake images, they find fake images as real with these very low percentages. So it is saying like all fake images are fake, almost all fake images are fake, etc. So this is the real detection of fake images. These are the false positives, okay? We do this adversarial generation where we just we approach deepfake detector as a black box, and we want to take the black box response, the confidence from the deepfake detector, and add it as a prediction loss to this autoencoder so that we can actually create adversarial samples. So when we do this adversarial samples, of course, we can also like L2 loss because we want to keep the image as real. When we do this generation, the real detection of fakes increased a lot. So it was saying almost all of the fake images are fake. Now it is saying 80% of fake images are classified as real. Okay, so this is the real detection accuracy of fake images. So we are actually fooling all of those deepfake detectors to think that fake images are real, just because we have this adversarial generation. So in this work, we want to emphasize that if deepfake detectors are trying to detect them blindly without looking any like authenticity signals or biological signals, this blind detection can be fooled very easily with adversarial generation. Okay, moving on. Another responsible deepfake approach is using deepfakes for privacy enhancement. So can we mask faces without obvious artifacts so that you see that whenever you see an image with people you don't know, they are actually people you don't know. They are deepfakes so that you don't grant access your face to other people. So for example, assume that A put an image of B and C all together into a social media platform, social photo sharing platform, but B and C are not friends. Do you think B should be granted access to see C's face? Or should they not see each other because they are not friends and they are not explicitly granted access to their biological information, which is their face? From the confirmation in the room, I see that you think they should not see their faces, right? Okay, yeah, so that's what we are doing. So we lift all of these faces to this face manifold with their face embeddings, and we try to find quantitatively dissimilar faces in the face embedding space so that we create deepfakes from those very far away, very dissimilar faces and use deepfakes. Now, you may say that we are still doing deepfakes, so what are those people doing, right? Like we are using these people to create deepfakes at targets. Well, these are already synthetic faces. These are already non-existing people. So we are not using other people to switch their faces, right? We are just like using already non-existing faces to swap with deepfakes. Well, at the end, what this person see, this person does not see the original version of original face of this person, and for someone that is not friends with any of these people, they see all deepfakes. So these faces are not at all these faces, and they are quantitatively not those faces. We also have, if you look at the paper, we also have a study about how much we are tricking face detection, face recognition algorithms, and we have maybe 80% misclassification rate for the identity of those faces. For responsible deepfakes, what we can do, we can also do 3D digital humans. For AR, VR, for the very first use case of deepfakes, we can actually create 3D digital humans, which are actually 3D deepfakes or 3D synthetic data. As you can see here, that one is me high-fiving with a friend of mine in 3D. So this was just like a one frame capture in 3D in our studio, but I animated it to be a high five. Anyway, so we can actually do 3D humans. For reanimation, for retargeting of 3D digital humans, maybe the most positive outcome of deepfakes. So we have this whole pipeline of future of immersive filmmaking. You can watch our SIGGRAPH presentation on YouTube. It is available. It includes deep learning models to clean, denoise, and segment point cloud for various use cases. Is this playing? Yeah, it's playing. Okay. For different use cases, automatic tracking, deformation, and morphing tools in 3D to replace and edit assets, or retargeting approaches for expression and post-transfer in 3D, or for here, like deep faking our old captures of people. Maybe another layer of excitement in that whole process is that our models, our 3D models are in the order of 20 times larger than the current state of our 3D data sets like ShapeNet. Lastly, I want to talk a little bit about media provenance. So we keep saying deepfakes, we keep saying synthetic content, we keep saying like how to find authenticity signals, but can we actually provide media throughout its life with this information, with this provenance information? So this whole project is not only about deepfakes, but it's about trusted media. And in the overview, the manipulated media detection or deepfake detection is the short-term solution for already existing media. But for the long-term solution, we want to have genuine media provenance. So we want to communicate the creation, modification, history to establish authenticity. For that, we want to have end-to-end chain of custody that starts at content origination all the way through a checkpoint, check at consumption of the media. So if someone is creating a deepfake using, let's say, like your favorite image editor or like favorite network, and it is for a good cause, right? Like the actor consented to it, the source and target knows it, and it is for some good purpose because there are good deepfakes around there. We want to provide that information. For that, there is the C2PA consortium. This is a consortium of many different companies like Adobe, ARM, BBC, Intel, Microsoft, Twitter, Trupic, and this is for creating open technical standards for publishers, creators, consumers, and the ability to trace the origin of different types of media. So media provenance will actually, hopefully in future, become so accessible and available for all synthetic content so that we don't even need to do deepfake detection. Okay, key takeaways. We learned that deepfakes are missing unique heartbeats. Deepfakes doesn't have hearts yet. We showed that the first method to detect deepfakes in the wild is FakeCatcher. I demoed the first real-time deepfake detection platform using OpenVINO, VNNI, AVX, all those Intel hardware accelerated AI shenanigans on third generation Intel Xeon scalable processors so that we can actually have real-time deepfake detection. We show that generative residuals have stronger discriminative features in PPG domain so that we can classify which deepfake came from which GAN. We show that responsible deepfakes have many different use cases in 3D or for anonymization or for adversarial generation, etc. We show that eye and gaze feature consistency in multiple spaces are also good authenticity signals. We show that non-impersonating deepfakes is possible with multi-source synthesis, and we show that deepfakes are useful in reanimation of 3D digital humans. So we have maybe the most cross-organizational team at Intel for the Trusted Media Initiative. So we thank everyone for being a part of a trustful future. Apart from the Intel team, we also acknowledge our academic collaborator, Umur Çiftçi, for his critical contributions to FakeCatcher and beyond. And thanks for attending our talk. Feel free to reach out to any of us and hope to see you in next event. So I can take the questions from the room or from the Q&A right now. Thank you.
So our standard first question is how many people in attendance in person and on Zoom are IEEE members? I think there's a poll that'll go up to ask them.
I have a question.
Yeah.
During your discussion, you talked about, for example, eye movements and how you can measure that. But it's a cat and mouse game, in my view, because processes are getting better and then detection is more difficult. So there's another metric that you can catch up, you can latch onto, but it goes back and forth. And eventually, I mean, I don't know where the breaking point is, but there's going to be a point, I think, unless you do another metric, then technology getting better and better every day. Where did this end? My question.
That's a great question, and I always get that question. And it's an arms race. Detection is getting better. Generation is getting better. And for the eye gaze-based detection, you are absolutely right, because the way that we are measuring the consistency of gaze vectors or the 3D points is actually a basic formulation that you can integrate into a loss function of a GAN. But that's not the case for FakeCatcher, because there are 3 reasons. I have a slide. The first reason is that the extraction of PPG signals is not differentiable. So you cannot just plug it into a loss function and backprop. Because you can't do that backprop, you cannot actually learn the exact formulation for PPG signals or PPG maps. If you want to not use the exact formulation for the PPG maps, but if you want to approximate that, then you need large ground truth PPG data sets to learn that approximation, and that doesn't exist yet. There are like 20, 30 people PPG data sets, which is not generalizable to the whole population, so you cannot learn a ground truth for doing supervised learning of PPG extraction. And even if tomorrow a hospital comes and say that we have like a 10,000 people PPG data set, you can learn it from there. We can still convert this PPG extraction to a probabilistic one, and instead of having those 32 signals from your face, we can randomly pick any part in your face, any point in your face, neck, or like forehead, etc., to extract those PPG signals. And in the authentic ones, in the original videos, it should still be the same, right? Because it is the authenticity signal. In the fake ones, then the generators need to create that probabilistic way to create all of those different PPG signals still consistent and coherent enough from everywhere in your face, which is like another layer of complexity. So for those reasons, FakeCatcher cannot be tricked yet. Beautiful question. Thank you. Yeah, you can.
So you mentioned 32 data points. I've been playing with AWS. There's a technology called Amazon recognition, where you upload an image and it will return back to you as an API, return data back to you. It'll identify what's in the photo. It'll say, oh, sorry. It'll identify if it's a male, if they're smiling, whatever the case is. And according to what they're showing, there's far less than 32. There are only maybe 6 data points that they're looking at. One on each eye, 2 in their mouth, 1 in the nose, perhaps 1 in the chin, and that's it. Just to further that point, I have identical twin sisters, and they can open up each other's phone. So it doesn't seem as secure to me as I hoped it would be.
That is for which algorithm? For which algorithm? For face recognition? For
Face recognition, yeah.
That's another topic that we that's not in context of FakeCatcher, but for example, for the anonymization project or for the adversarial generation, yes, that may be a case. But in that case, we are working with like different face embeddings, and those face embeddings are extracted in a more complicated way that is not just like a face ID. And in that, we are trying to select those face embeddings from the furthest face in the synthetic face manifold, so that it is decreasing the face recognition as much as possible. Now for FakeCatcher, these 32 PPG signals are not your regular data points. How do I go there? Okay, I will try. Just sorry. Can I actually? Okay, let me go to that slide, sorry. Okay. From current slide. Okay, so you see, this is the, when I say 32 signals, this is a signal grid that we extracted from. So it's not like eye and nose and etc. That's for face recognition, but for FakeCatcher to extract these signals, this is a 32 signal grid, and from each of these cells, we are extracting a PPG signal. Then we are using those PPG signal to create the PPG map and then the PPG cell, and we are doing the heart rate based defect detection based on this. Of course, thank you. Any other questions from the room? Else I will go to chat.
So we have a question from the Q&A. The question is, do the classification accuracy results vary by video resolution and or encoding or streaming format?
Very good question. Yes, we have those. Oh yeah, of course. Sorry. Does those FakeCatcher accuracy depend on the resolution and resolution and what?
Encoding or streaming format?
Oh, encoding or streaming format, yes. Both the classification accuracy and the performance actually depends on those. So for the resolution, we have we have a follow-up paper that is hopefully coming soon, depending on what resolution that we try. Of course, with the if the video is downsampled and a little bit blurry, the accuracy drops a little, but that's downsampling is actually a linear operation that you do everywhere on the face. So even if the signal is corrupt, the corrupt signal on your left cheek is still correlated with the corrupt signal on your right cheek, because the same linear operation is applied to all of the PPG signals. But for the fakes, even if you apply those like different operations, then the inconsistency of the PPG signals remain the same, because it's not a corrective operation, right? So the real and fake accuracies are still relevant in terms of how we do. And on top of that, it's not like an exact heart rate extraction. There's a deep network doing that, so we are a little bit more robust to those like resolution changes. For formats, for encoding and streaming formats, the streaming format is mostly important for real-time performance. So for some of those formats, we can still do real-time, but the frames per second drops a little bit because of the convergence between the different formats or because of the streaming quality. And for the accuracy, it's not actually that different as long as it's not a very high compression. So as I said, like we have a follow-up journal paper that is coming up, and in that one we looked at the 3 different quantization levels for the compression. And if you train on no compression and test on like mid-level compression, then it is still like okay accuracy, around like 85% accuracy. But if you train on originals and and test it on like Q40 quantization, then you lose things because PPG signals are very sensitive to these compression artifacts.
Thank you. We have another question from online. It says, now that the PPG technique is publicized, what will prevent a deepfake generator to produce realistic PPG signatures?
I think that is already answered by your question, right? Like I already answered that, but I can go back to that slide and show it. Oh, I can do this, yay, sorry. I just realized I can do this, okay. Yep, as I said, there are 3 reasons why PPG signals cannot be replicated yet, so maybe I will pass this. Very good question. We actually try to look at the cause of these errors more than looking at different metrics, but OROC and other ones are also in the paper for some of them.
Okay, this is a question about gaze detection. Are there medical conditions which cause real people's eyes to misbehave like the fake eyes do?
That's a beautiful question. And maybe it was my fault to generalize the eyes like that. I should not have generalized. So especially like we talked a little bit. I used to work in Oculus about understanding human behavior in VR headsets. And in VR headsets, we use eye detection a lot, right? Like gaze detection a lot. And in that case, like working on that data make me realize that especially for such an task of gaze detection, there is no way to generalize all the population. Like if an algorithm comes and says we are like generalizing to like, I don't know, 95 of the population, that's like something to applaud for. So especially for eyes, like people have so much eyes, and gaze data, actually the 3D gaze data can be used as a fingerprint too, because it is very unique to everyone. In that case, of course, like if there are some eye conditions and like medical conditions that your eyes are actually not coplanar, but you still have some understanding in your brain functions that you understand what you are saying, or some, you know, like some people have gazes like not converging planar on the same plane, but like diverging, but they still see around and they still understand. So it is definitely based on the training data. And if you have those eye conditions in your training data, then the network that you're training on, that data will be inclusive to those conditions. But if the training data does not have those conditions, even if a few samples, then of course you will be omitting them as fake. And this is like why like all of us are working on responsible AI techniques to be inclusive, to be fair, to not exclude such long tail distributions, but real humans as fake. So that was a beautiful question, and I hope at least being aware of that problem is something that we can do for future.
Okay, did you experiment or test GPT-3 models, or just GAN?
I haven't seen, I don't know how GPT would be used for deep fakes. Those are mostly for language models that you create fake speech. If the question is like, if we looked at deep, if we looked at other domains as like fake speech, fake audio, no, we have not yet. We have some multimodal approaches baking. They are not published yet, but we haven't looked at language models or like fake speech or fake text or, you know, like all those misinformation that is coming from fake news. We haven't looked at them yet. We are looking at mostly like face images and videos. Okay. I thought they were able to see the questions in the chat. I'm really sorry. I will repeat the questions. I'm sorry. Okay. Oh, okay.
Okay, are there any analogous methods to those presented in here for faked audio? Are there any current plans for an audio classification platform?
I'm looking at the name for who asked this question. If you are not already working with me, come work with me. Where's the camera? No, I'm joking. So yeah, we are actually looking for multimodal approaches right now. So all of those biological signals that I talked about, they are not like those like magical approaches that you extract only from the video, but you can also extract them from speech, from audio, from breathing patterns, etc. And we are looking most of them to go through those like multimodal approaches, not just like the image domain, but the other domains too. So yes, currently, so that's the part that we are working on. But currently, there are, of course, there are some approaches, as I said. I think I already mentioned the phoneme mismatch. For example, like all your mouth movements have an associated sound that comes from them. So there is actually a paper. I'm sorry, I don't remember the authors of the paper, but just look for like defect detection phoneme mismatches. So they are trying to train a deep neural network to actually associate those like mouth movements, like window by window, to the actual sounds that are coming from those mouth movements. There's another one that is also multimodal that are looking in emotion in deepfakes to understand whether our sounds and how we speak and our mood and gestures are actually coherent to represent one emotion, versus in fakes, maybe the sound or speech doesn't have that emotion, or face doesn't have that emotion, etc., or gestures does not have the emotion. That's like a maybe like a higher dimensional space to explore, but it is still a multimodal approach because they are looking at those multiple signals.
And this one is more of a comment that you've probably addressed already. This comment is, it seems to me that a GAN could mimic the behavior, for example, eye movement, facial muscles, etc., by taking the information from a real person and using it on an artificial image. Eyes, lips, movement, everything could be taken from a real person and coalesced to create a fake that uses real dynamic behavior. It seems to me that such a fake could be difficult to detect because you do not have a single real person against which to compare.
Okay. Thanks for the comment. I think it's a little bit more towards the mixing approach that I mentioned. Instead of like taking different face regions from multiple people, like taking different audiovisual signals from different people would also create a mixed person, which will be harder to detect maybe.
And the person who submitted the question in regards to the GPT-3, a little bit of a tongue twister, they actually sent a link and it's about image GPT. And it said, we find that just as a large transformer model trained on language can generate coherent text, the same exact model trained on pixel sequences could generate coherent images, completions, and samples. By establishing a correlation between sample quality and image classification accuracy, we show that our best generative model also contains features competitive with top convolutional nets in this unsupervised setting.
Thanks for sending the link. I completely forgot about this way of using GPT. Yes, we haven't yet tried on GPT generated images, the deepfake detection, but I want to also mention that this is image based, and all FakeCatcher and gaze-based detection and source detection are based on videos. So when we have video GPT, maybe we will try on that.
And I think those are all the questions that I'm seeing from online. I don't know if anyone else in the room have additional questions.
I'd like to hang on something. Mention something in your credits. You mentioned you're doing deep learning using Intel Xeon cheap processors. Perhaps this is an opportunity to market yourself, but most of the, well, NVIDIA has gotten a lot of publicity for their GPU processors being used for deep learning. Compare and contrast the use of Intel Xeon with NVIDIA for deep learning.
Ooh, that puts me under pressure. No, I'm joking. So maybe something I forgot to say is that all this inference that I mentioned, that we can go up to 72 concurrent detection streams, is on GPU, is on CPU. It's not on GPU. And the beautiful part of this is that this framework is one framework, one open visual cloud software stack for GPU, CPU, VPU, which architecture you have, you can go deploy this on. So that's the beauty of this platform. That maybe if I have it, I can show it. I wish I had that slide. That was the marketing slide that I excluded. Sorry, marketing people. So I need to find it. I don't have it. Sad. Okay. I can talk about it here. So all these AVX and VNNI and OpenVINO AI models, etc., are in this pipeline using Open Visual Cloud in one Docker that you can deploy into any platform that you have, and it will have this. It will still have the same acceleration, same optimizations for running real-time defect detection. I think that's a beautiful way to show it. And in addition, it's not only the AI models, but the inference blocks and the computer vision blocks and some Python instructions are also optimized with Intel IPP and OpenCV. And you can, based on how much real time or based on how many concurrent detection streams you want to do, you can actually very easily convert these OpenVINO models to int 8 or int 16 from FP32, so that you can just like measure, set that trade-off between the accuracy versus the how many you want to run concurrently in real time. So here, for example, we have face detection and landmark detection models as int 8 and the PPG classification model as FP32. But if you want, you can also like convert that model to int 8 and have even more accurate, more performance than the one that we have here. So I think those customizations, having it in a like a completely open sourced software stack with Open Visual Cloud, and like actually like except this PPG pre-processing and PPG classification, everything is already open source. You can go download OpenVINO AI models. You can go download Open Visual Cloud software stack. You can use OpenVINO. Like you can do all of them except these PPG processing and PPG classification. And the reason that we are not open sourcing those PPG classification is just to following up your question again and again, just we don't want to enable the bad actors to actually reverse engineer and like create something that we can that can create deepfakes with good PPG signals or good enough PPG signals, because I showed you that like we can create we can have adversarial generation for for fooling detectors, right? Why, if you have the PPG model as the black box, can you actually learn how PPG classification works based on the black box response of the FakeCatcher model, right? You don't want to do that, so that's why we are not open sourcing the PPG models. But if you have, so anyone here or anyone in the Zoom, if you have a use case for real-time defect detection, or even not the real-time, but like defect detection, we are open to share our platform. We are actually talking with customers about how we can deploy our fake detection platform into their workflows, and we are very open to it. So come find me. Thank you for the question.
I have a question for you as well. Can you comment on how large a team it took to do this work? Since individual contributor, or is there a large team working on this with you?
That's a very good question. Let's go to the credit slide. And even my credits here doesn't give enough credit because I cannot list everyone. FakeCatcher is actually my and my collaborator, Dr. Çiftçi's baby. So the idea phase and the first prototype took only 2 people for FakeCatcher for initial like PPG experiments, etc. After that, to take it from that only paper or only just a research idea or research paper to this like the first real-time defect detection platform, it took a ton. I have so many collaborators. First of all, like Karl Marshall, Satyam, they were in Intel. They are not in Intel anymore, but they were the initiators of the trusted media. We have a whole like Intel fellows and seniors that supported us for going through all of these phases of the project. Then I have the demo team, like Kevin, Shasha, Jerry, Anthony, Pengfei. I cannot list Surbi. I cannot list anyone. Sumit. I cannot list anyone. But everyone. But like it really took so many like architects and then optimizers, then engineers and research team, and like it really took a lot of people to create this real-time platform. But yeah, if I need to thank, I'm thanking everyone. But Dr. Çiftçi is like maybe one of the most dedicated people that I know, that dedicated his life to FakeCatcher maybe, and source detection and eye gaze detection. So I think he deserves as much credit as I do.
How often is FakeCatcher running in trying to do detection? Is it all the time? Do you analyze trends with other current events to see if there's a rise in fakes being detected?
Yeah, that's a very good question. So whenever there is something going viral, we actually run it. We actually see, oh, is it finding, etc. So maybe the most recent example that I can give is that if you remember, there was the fake Zelensky video going around, misinformation about the Ukraine-Russian war, and like maybe if you, I don't know whether you watched the video, but if you watch the video with an eye like us, because we keep seeing fake videos everywhere, you may say at the first glance that, yeah, it doesn't look very realistic, or the head is like this, or the resolution is like that, etc. But put yourself in place of those people that are like looking for information, like hungry for information because they are running for their lives, and they suddenly see that video and they believe it. Like that is like a, like, I don't know, creating that video is like really not human at all. And in that situation, all of us would believe whatever we see, right? So anyway, we took that video, we ran FakeCatcher, it gave us 98% accuracy for saying it is a fake video. But for example, I don't know, whatever platform it was, it took people to mark it as like, oh, like this is fake, or this is junk, or this is like whatever, like the take this down button, you know, like the people keep clicking on that button, and after hours, after days, I don't know, it was taken down from the platform, right? But between that time, from the ingestion time to take down time, so many people saw it already. So many people believed it already. So many people acted on it already. So what we claim is that if there is at least some mark or some confidence metric in the ingestion time, like whenever I'm uploading a video to a platform, it goes through that pipeline and says that, okay, with 90% confidence, this is real, or with 95% confidence, this is fake, etc. And still, you can still show it to the user, but show it with that confidence, show it with that label that came from an algorithm or multiple algorithms to provide algorithm consensus. Say that, okay, like we run it through 5 detectors and all 5 of them said like over 95% accuracy, it is fake. And then no one will believe that the Zelensky video. probably, hopefully, right? So that was a recent case that we run. And whenever there is like a new parody or like, you know, there are so many Trump videos that are fake, we keep running it, FakeCatcher on it. And whenever we find something that is like, oh, this looks really real, FakeCatcher says it is fake most of the time.
You envision a time when quite literally do you envision a time when everything posted in social media, for example, will require this authenticity signature? So otherwise, what can we possibly believe? And even forget social media, there are even commercial applications. Even a CEO just speaking to his employees in an internal discussion that can have very deep implications as well.
Hopefully, because this is becoming a real problem, and especially for I mentioned in the beginning, like for adult content, there are like millions of videos that are deep fake, because like, you know, whenever there is like an evil use of a technology pops up, it is used in that domain. I think there was a report from 2019 that 96 or 98% of all deepfake videos are for adult content, for example. So I think this is becoming a problem. It has been used in like fake court evidences, in like fake coup attempts for political campaigns, etc., etc. So as I said before, like now detection is maybe a short-term solution for existing media, but for a long-term solution, media provenance is needed. And for any software that is creating deepfakes, may it be GANs, may it be auto-encoders, may it be some commercial solution. I think Adobe has like neural filters, etc. It's not deepfake, but it's actually a neural network doing some manipulation on the image, etc. There needs to be that like authentication stamp or watermark that shows the provenance of the media. Now, taking that media provenance all the way from hardware is hard. You cannot go and put a watermarking chip to all the cameras existing in the world. So instead of going all the way to the hardware, people are trying to find these like intermediate solutions. For example, like C2PA is for created content. It is a coalition for content creation. I forgot, I'm sorry.
What NFTs are all about? The original, the authentic one, not a copy of it. I mean, isn't that kind of the same thing? I think?
That's a way, yeah, using like NFTs or creating some blockchain-based authentication for media. That's a way, but that's again for not all the media that is created. That is for most unique art pieces. It's not for every deepfake that we have around or every deepfake Trump parody that is on YouTube, you know. There needs to be some more simpler but still secure approach for providing that media provenance.